Hello, today we will be presenting our ACI Ecoconcrete competition. The group members are Sophie K, Bree D, Lacey N, Frida A, Will S, and Alexis A. We have been advised by Dr. Durham. This video report contains our project objectives, our base case scenario design, and our alternative case scenario design, as well as our life cycle analysis, which will help determine our durability, performance, and the major factors affecting our outcome. We have more details provided in the written report that has been submitted as well.
The project objectives are to define a sustainable concrete mixture using low environmental impact materials that will have equal or improved durability. And this will be modeled by creating a base case scenario that will contain a conventional 100% cement mixture and compare relative to a alternative case design, which includes sustainable improvements.
The material selection was based on the criteria outlined in the competition rules, as well as material location, transportation, and environmental impact. The water to binder ratio is 0.4 and the nominal minimum aggregate size is 5 millimeters. For the base case scenario, aggregates constitute 77% of the total mass of the concrete mixture, and coarse aggregates make up 53% of the mass of the total aggregates. For the alternative case scenario, 35% of the cementitious materials are supplemented with Class F fly ash, and aggregates again constitute 77% of the total mass of the concrete mixture.
The use of Class F fly ash as an SCM aids in producing stronger, denser, and more durable concrete. It also increases the workability and lengthens the setting time. Fly ash is more cost-efficient than Portland cement, and more cost efficient than both blast furnace slag and silica fume, which are other SCMs. Class F fly ash used in our alternative case scenario is from the nearest supplier, which is Boral Resources at Plant Bowen in Stylesboro, Georgia. This is located about 178 kilometers from the batching location, which is the UGA Strengths Laboratory. The aggregates and the cement will both be obtained for the BCS and ACS mixtures from Thomas Concrete in Athens, Georgia, which is about 9 kilometers from the UGA Strengths Lab. Regarding the Ecoconcrete calculation tool, this tool was used to find our environmental impacts by entering in the base case scenario and alternative case scenario mixture proportions, as well as the transportation distances and categories for each material. In conclusion, this gave us a summary of 5 different categories of the environmental impacts for the base case scenario versus the alternative case scenario, which we will go further into detail explaining on our next slide.
When analyzing the life cycle analysis, 5 major environmental factors were examined: global warming, ozone depletion, fossil fuel depletion, carcinogens, and ecotoxicity. We had an average overall potential environmental reduction of 16.9%. For global warming, the potential decrease of CO2 emissions was reduced by 30.3%. And most of this improvement for global warming actually came from the production of Portland cement itself, as only about 10% of the CO2 emitted in concrete production comes from transportation. It is estimated that for every cubic yard of cement produced, 400 pounds of CO2 are emitted. Therefore, reducing the amount of cement used by 35% from 400 kilograms per cubic meter to only 260, we can expect a 30.3% reduction in CO2 emissions. Chlorofluorocarbons, or more commonly known as greenhouse gases, are also a byproduct of Portland cement production. And these are what causes ozone depletion, and by replacing 35% of the cement with fly ash, an estimated reduction of 18.7% of ozone depletion can be expected.
Fossil fuel depletion accounts for a reduction in 21.4% in that category. And that is due to the fact that using a recycled fly ash reduces the amount of energy needed to produce and extract the materials for Portland cement. Another category is a reduction of 16.6% in carcinogens. Portland cement concrete is known to contain several hazardous carcinogens, which are typically released in the form of dust exposure. By replacing Portland cement with fly ash, we're essentially reducing the amount of carcinogens in the mixture. And our last category is ecotoxicity, which is actually an increase in 2.4%. Ecotoxicity is essentially the measurement of how humans affect the microenvironment. The reason for the increase is because fly ash is a byproduct of the coal industry, which typically contains higher amounts of heavy metals. These metals tend to seep into the soil.
From the data collected from the Life 365 application, the service life of replacing 35% of cement with fly ash, we can expect to see an increase of 8.8 years of service life from 11.9 years to 20.7. The initiation period is also increased from 5.9 years to 14.7 years. The initiation period, which is the number of years it takes for the corrosion of the steel to be initiated.
Substituting Portland cement, which is the constituent in the concrete mixture contributing the largest environmental impact with 35% Class F fly ash, exhibits a promising sustainable improvement. It enhances the desirable properties of a 100% cement concrete mixture by reducing carbon dioxide emissions, improving the total environmental impact by 16.9% and improving economic efficiency. It is important to consider, however, the 2.4% detriment in ecotoxicity, but since the supplementary cementitious materials release more heavy metals into the environmental elements compared to cement. However, in all, the alternative case design is recommended for the Athens, Georgia region due to a clear improvement in sustainability and in general benefits modeled by the alternative case design relative to the base case scenario.